Okay, so next we look at the surface integral. The surface integral is just like the line integral, but the difference is for line integral we deal with the single integration, and it is the function is integrated over the curve. Okay, whether that one is on 2D or on 3D. But surface integral, we instead of we have a single integral, we have double integral and integrated above the or over the surface. Okay, as from the name here, it's surface. So we integrate the function. So normally the function is called density function over the surface. So what is the application or the physical meaning of the surface integral? So for your information, the surface integral are commonly used in multiple areas of physics and engineering. Particularly, they are used in finding this kind of problem. For scalar field, we can use the surface integral for scalar field to evaluate or to compute the mass of a surface. Do you remember that you use the double integral to evaluate the mass of lamina? So actually, the general form of the mass is from the surface integral. Okay, because for the line, the double integral that you have learned before this, you can use the double integral to evaluate the mass of lamina. So now we have a more general case. Instead of the lamina is lying on the xy, it can be lying on the any other plane. Then we call that as a surface. So we can use the surface integral to evaluate the mass of a surface. And also we can use that to evaluate the center of mass and the moment of inertia of a surface. Okay. So then we can use the vector field to, using the surface integral when your function is a vector field, we can evaluate this kind of problem. So we can compute the gravitational force. We can use the surface integral for vector field in calculating the flux. Okay, the flux and the mass of the flux flow, or we can say that the fluid flow or flux and the mass flow across the surface given. So in the information, they should give you the information regarding the surface. The equation of the surface, and also they must give you the vector field here. So the vector field that passing through the surface, then we can evaluate the flux. Okay, so these are some of the application or the physical meaning of surface integral. Okay, and in general, surface integral is given by in this form. So in line integral before this, we have the single integration, and we have C instead of sigma, we have C, right, curve, and we have the same density function here, whether just xy or it can be xyz. And for the previous line integral, we use the d as a small s. For that small s is for arc length. But now we have a capital S, so the capital S here is not the same as the small s that we were using in line integral. So this one is a part of the surface sigma, where we call that as a ds, or we call this as a patch of the surface. So now S here is telling you about the surface, where the surface here is given by the equation of sigma. Okay, if your function here is equal to 1, where you have this form, so we can actually evaluate the surface area. So let's say you are given because now we are talking about the surface, not the region, right? So surface here, let's say you have a cone, you have a sphere, then we can evaluate the surface area of that cone and the surface area of the sphere. For example, you have a cone in this shape. So this is your cone. Okay, and you can have the cone here, and you can evaluate the surface area of this cone using the surface integral when your density function here is equal to 1. Okay, that is the general form of the surface integral for scalar field, and the general form of the surface integral for vector field. We still have the double integral and we still have the ds, but since now we are dealing with the vector field, so instead of we have a small f, so if we understood that the small f is for scalar function, but the capital F normally we treat this as a vector function or vector field. So when you have a vector field, you cannot easily multiply by any other vector, then you have to apply the dot product here. Okay, and the ds here, the information should be in the vector form as well. Okay, but it can be simplified into instead of here we have the ds in vector form, so now we can convert into a scalar form by using this. I mean, it can be, I didn't show it here, you can just directly use that. So f dot ds can be represented by the f dot n ds. So what is n? N is the normal to the surface. Remember on the previous lesson I have teach you how can we evaluate the normal vector to the surface using the gradient, the gradient of the function given. Okay, so now meaning that in this calculation we have to use the previous lesson, which is you have to be able to compute the normal vector to the surface, then you can use this formula. But actually for your information, we have a more simpler calculation that I will show you later when we go to the example. Okay, so for the surface integral for the scalar field also can be assume we can calculate the total amount of the rainfall on a hill. Let's say your hill is in a cone shape, so meaning that your surface, your sigma, is given by the cone equation, so we can evaluate the total amount of rainfall. It looks like we can evaluate the volume of the density. So this is another physical meaning, depends on the information provided. Okay, okay, so now about the computation. Okay, just like line integral, we divide our calculation into two different problem, where we start with the surface integral for scalar field, and then from there you have to apply some some calculation, some steps in order to get the result. Okay, and then after that we will look at how can we compute the surface integral for the vector field when your information given is in a vector form. Okay, so now we want to integrate the density function over the surface sigma. So where is your surface sigma? So in general, let's say you are given a surface, should be in 3D, right? Okay, sigma should be in 3D. Okay, so we can see that if you have this particular form, so let's say you choose that, let's say normally when you sketch a surface, you have to provide the orientation, right? Let's say I use the standard orientation X, Y, and this one is Z. So it looks like your region is lying on XY plane. So then we can say that the region of the sigma of the surface lie on the XY plane. Okay. So now about the computation, how can we evaluate the surface integral? Actually, in general, there are two different methods. Okay, the first one, that the thing that we will apply. So we deal with the XYZ. Okay, and the second one, you have to find the parametric equation of the surface. Okay, but the thing that I will focus in here is I will use only this particular computation, because that one is more easier. Okay, but for the second one, for me the hardest part is you have to find, let's say you have your sigma, your information about the sigma, the surface is given by the cone of the z equal to square root of x squared plus y squared. So now you want to use the parametric, you want to use the parametric surface where you convert the x, y, z into the another parameter, two parameters. So in this case, because you have a cone, so the most possible parametric equation here is in terms of r theta, which is polar or cylindrical. In 3D we call that cylindrical, right? So in this case, how can you convert that? So the simplest one, we can say that x is equal to r cos, that is from polar, right? And y is r sine. Okay, where you have this one, x is r cos, y is r sine, and your z is equal to r. That is from the cone equation itself. So this is your parametric equation. As you can see, your parametric surfaces or parametric equation for the surface is depending on two variables, r and theta. So next you have to find, you have to deal with the r and theta instead of x, y, z. But in this calculation, I'm not going to use this. Okay, I'm not going to use the parametric surface. So I will use only this one. Okay. Okay. So now we look at the definition, the standard definition of surface integral. So this is a general form where okay. So okay, as I mentioned before, we start with the scalar function. So your density function is in terms of x, y, z. Okay, and now how can we say this? This is the surface integral of the function given, or density function given over the surface sigma. Okay, and S here is the area of the surface, or ds itself is the area of the patch of the surface. Patch means part of the surface of sigma here. Okay, so now just like line integral, you have to be able to get to convert the ds in terms of something that you're familiar with. Okay, because of normally when we have a double integral, so for double integral that we have learned before, you are given a function. Okay, you are given a function or the integrand, whether x, y, z, and so on, and you have the dA at the back, right, and over the region R. So you will see this after a few steps. So now the problem in surface integral, how can you provide the step to get this kind of form? Okay, so now you need to get you need to know the formula of ds in terms of dA. Okay, so in order for you to convert the ds into dA, so in general, this is the formula that you need to implement, to apply. But before we use that, we have to understand what is the del z del x, what is the del z del y, and how can this one to be equal to 1. Okay, so firstly, you have to look at your surface. What is the equation of the surface? So now you ask yourself, okay, let's say I'm using the cone. So normally the equation of the cone is given by the square root of z equal to, right? Z equal to the square root of x squared plus y squared. Okay, but sometimes they can change the equation, right? But still a cone. Maybe they can give us x equal to the square root of y squared plus z squared. So this one also a cone. But your cone here, if this is the equation, then this is supposed to be x and this is supposed to be y and z. Okay, but in this case, let's say we have a standard cone where for that equation we have z here, and we have x, and we have y. Okay, so for this particular equation, where the equation is given by z is depending on the x squared plus x and y. So in general, we can represent this equation or function to be z is a function of xy. So now you can see that, okay, your phi here can be represented by z equal to the function of xy. So for this particular sigma equation, we can see that normally the region is lying on xy plane. Okay, the region is lying on xy plane. So then what you can do is, now you want to get the ds, right? So the ds here, so it should be actually this is a surface. Okay, so the formula here is actually x zx squared plus zy squared plus z squared. That is actually the original formula to get the ds, So in this case, zx, you have to differentiate this function with respect to x, just like this one, and this one you have to differentiate with respect to y. And when you differentiate z with respect to z, and your answer will be 1, right? Because z, you differentiate with respect to z, and the answer is 1. So that's why we have 1 here. Okay, so then your ds next can be transformed. So when you plug in ds in terms of dA, so now your ds looks like, and then you can now convert from ds to dA. Now we have a standard double integral where once you have dA, so automatically you have the region here. Okay, so the procedure to compute the double integral over the region is exactly the same that you have done in chapter 3, where you managed to convert the ds into dA. Okay, so now look at the formula in general for the specific function or the equation of the surface sigma. So the first one, if your function is in terms of xy, so your formula is the same as that I showed you before from the example here. If you say that your function is in terms of xy, so your region must be lying on xy plane, and you have meaning that all your information after you substitute the ds in terms of dA, there are only x and y, no more z. Okay, because when you have the double integral, the total number of variable that can be possible in the expression only 2. Okay, so that is a concept of the double integral. Okay, now let's say your function of sigma is given by y equal to something. So let's say your function is given by y equal to x squared plus z squared. Okay, so the simplest version that you can have is you have y equal to, actually you can have the x, so let's say, but then you have to rewrite, so x squared is y minus z squared, and then your x is plus minus y minus z squared, but then your surface is divided into 2. So in your calculation, you have to consider both of them. The first one is the surface of the positive square root, and the second one you have to find the surface integral for the surface of negative square. So you are wasting your time. Okay, so please don't need to waste your time. If you have a more easier way, then you just proceed. So in order for you to proceed without splitting the surfaces here into 2 parts, so we can just have y in the function of x and z. So since our function is in terms of exact, so we understood that the region that we have to have here is lying on exact plane. So depends on the variable here, exact. So you have exact plane. So how about your formula to convert the s to dA? So now you have y, so you have to differentiate y with respect to x. So you have yx squared, and you have to have y, and you have to differentiate itself. So y or dy over dy. So this one becomes 1. And then y you have to differentiate respect to z, so you have yz squared. Okay. And next, let's see your your function of your sigma of your surface is in terms of yz. So let's say I'm using the same. We have a bowl where the bowl is given by x equal to y squared plus z squared. So in this case, we can represent this in more general, where x is the function of y and z. So your origin must be on yz plane. Okay, so to get the ds in terms of dA, so you have to differentiate x respect to x and give you 1. And then differentiate x respect to y, you have xy squared. And differentiate x respect to z, you have xz squared. Okay, so that is only the thing that you have to do first before you manage to reduce, from surface integral where you have the density function in terms of ds over the surface sigma. So after you substitute this, and automatically you have dA. So now it's become f in terms of scale. Let's say now you have the situation here, you are using where your surface function is in terms of xy. So we should know that after you convert ds into dA, so the only possible variable allowed in the double integral must be only x and y, so no more z. So now that your function then become x and y only, and dA. Okay, so from ds you have dA over the region R. Then how can you get this? So using this formula. Okay, just like a magnitude formula, right? Okay, so now in order for us to get more understanding, so we look at the example. But please don't look at the answer yet, because I'm sure that you don't understand at all. Okay, so please focus on the question first, where I should continue on the next video because it's already too long.